Welcome back. We have talked about classical statistics, all the machineries, to calculate thermodynamic quantities via the partition function and so on. We know that the partition function actually gets carried over to quantum statistics as well, and we have used the grand canonical partition function. We could use the canonical partition function as well, but it is better to use the grand canonical because of these number, the constraint on the total number of particles, and that the ensembles are allowed to exchange number of particles in addition to energy. So, we have looked at Bose-Einstein statistics, and the important thing that comes along with is the Bose-Einstein condensation, which happens in 3D for non-relativistic dispersion like a k square dispersion, E going as k square, and we have seen that the ground state is macroscopically occupied below a certain temperature, and this is called as a Bose-Einstein condensate. And there are certain properties associated with it, such as the pressure is entirely due to the excited state occupancies or the particles that occupy the excited states, and the ground state exerts no pressure at all. And for a Bose-Einstein condensate, it's only half of the classical pressure, which is very less. Then we have seen other quantities or other physical properties such as internal energy. We have looked at the specific heat and looked at discontinuity in specific heat and so on. Now we will talk about Fermi-Dirac statistics, that is the other set of quantum particles which obey Pauli exclusion principle. They have antisymmetric wave function, and they correspond to spin angular momentum being half integer and so on. Okay. So, they come in this Fermi-Dirac statistics. We have introduced that. Now, we will talk about various properties of this, and we will try to cover these few things that are written here in this class. We will talk about degenerate free Fermi gas. So, what is the degeneracy limit and what does degeneracy mean actually? Then we will talk about the Fermi wave vector, Fermi energy, the ground state energy and pressure of a free Fermi gas. We will of course talk about the Fermi-Dirac distribution, how it looks like, that is the average number of particles occupying these single particle states, how they look like, and talk about the chemical potential, derivation of specific heat and so on and so forth. Okay. So, there are a number of things that are on the cards. And once we are done with this, we will get into a little more involved calculations of one is that we will calculate the paramagnetic susceptibility of these free electrons. This is distinct than the Curie's law, which you are aware of, which goes as 1 over T, and will show that the susceptibility is actually independent of temperature and depends on the density of states at the Fermi level. In addition to that, we will talk about stars, particularly white dwarf stars, which can be seen as examples of heavily degenerate Fermi gas at these are very important applications of Fermi-Dirac statistics. So, we would still be talking about non-interacting fermions and their properties. Okay. So, let us see that what is this degeneracy and how it plays a role. And so, this whole idea of studying this Fermi gas is that we should be able to apply it on metals. So, metals are there are a lot of free electrons which are not bound to the atoms, and they are ready to take part in the conduction phenomena when you apply voltage on the material. So, for metals, typical mass density. So, mass density is of the order of few grams per cc. you can convert that into kilogram per meter cube and so on. And so that tells you that with this kind of a mass density, the number of electrons per unit volume is of the order of 10 to the power 23 to 24. So, let us write 10 to the power 24, and this tells you that if you have this kind of a density. So, this is like a density, and the density is like your total number of electrons divided by volume. So, if you take them to be spherical and consider the radius of those electrons to be around say the volume is 4/3 pi r cube, where r is a radius. R is also the mean distance or the average distance between two electrons, assuming that they are just touching each other. So, that gives you an average a distance between electrons. So, we are simply trying to calculate the order of magnitude, and this let us call it as R average, and this should be of the order of an like angstrom or 10 to the power minus 8 centimeter. So, this is a typical inter-electron distance in a metal. Now, when you need the classical limit to dominate, so the classical limit would dominate if this condition is made, that is R average should be much greater than lambda, and this lambda is nothing but the thermal de Broglie wavelength, which we have written several times earlier, and it looks like this at a given temperature T, which is T is in the denominator in the square inside the square root. So, this tells you that this is equivalent to T to be much greater than H divided by 2 pi and m k and R average square. And if you put R average etc. So, if you put mass to be mass of an electron and R average to be around this 10 to the power minus 8 centimeter with the value of k and this Boltzmann constant and H, then what you get is that you get a R average to be at so R average is of course 10 to the power minus 8. So, you get this T to be even much greater than 10 to the power 5 Kelvin, okay, or at least we write that T to be 10 to the power 5 Kelvin. So, even at room temperature, okay, which is known to be our classical limit from the discussion that we had so far, it looks like that the room temperature is far lower than this temperature. So, what you would have imagined as a classical limit, can be the room temperature, that is it should still be able to be taken as T equal to 0. So, this is like saying that the ground state is enormously degenerate. Okay, let me sort of make a box of this. It is an important statement. So, what we have said is that if you really want that classical limit that we have applied to say bosons or any quantum particle, if you apply that to fermions and particularly to electrons, then what will happen is that the temperature at which you want the classical limit to set in, that is the classical limit would be valid at a temperature which is 10 to the power 5 Kelvin, more than that in fact, okay, which means that room temperature, which is 300 Kelvin, which is just about 10 square, that is 10 to the power 2 Kelvin, can still be taken as room temperature. So, all temperatures all the way up to say room temperature can be considered as 0 temperature, because the scale that you consider with, or the scale that you want your quantum gas to go into the classical regime is extremely high. And we will show that in fact the TF called as the Fermi temperature is precisely of this order for all metals, okay, all known metals like aluminum, copper, and various other things that you are iron, nickel, etc. This Fermi temperature is very large, it's 60, 70, 80,000 Kelvin. For example, for copper it's around maybe around 70 to 80,000 Kelvin by putting in all these values that we have just done. Okay. So, I think the argument is clear that almost all temperatures that are under consideration in which experiments take place can be taken as 0 temperature, which means very low temperature, and in very low temperature the quantum effects become very important, and we should consider these electronic systems as quantum systems even at room temperature or even a little more than that. Okay. We talk about room temperatures to be 300 Kelvin, even if you talk about 350, 400 Kelvin, it really does not matter. Even 1000 Kelvin is like 3 orders of magnitude, 2 to 3 orders of magnitude lower than the temperature scale that we have found out where the classical limit would be valid. Okay. So, this is something that we need to understand, and we are sort of, let me do a simple minded analysis of these Fermi systems, and we can start with say a particle in a box. Okay. And you are all well aware of this problem. Now, I just talk about a 3D box. Okay. So, the box is 3-dimensional box with x going from 0 to L, y going from 0 to L, and z going from 0 to L. So, okay. So, you can imagine a box, a cubical box, but all its the sides infinitely going large, so that the particle is really contained in between 0 and L. So, the potential is infinitely large. So, we still have a box like this. Okay. Call it x, call it y, and call it z, and the particle is contained in this, and it cannot escape because the walls in all directions have infinite potential. So, this problem is well known. I mean, you have these epsilon k equal to h cross square k square over 2 m, and when you solve this, so k square is equal to kx square plus ky square plus kz square, and you have kx going as, so this kx etc. are quantized as 2 pi over L nx, and similarly for ky with ny and kz for nz. Okay. So, the quantization of this problem can be expressed in terms of these quantum numbers, which can take values all integer values starting from 1. There can't be 0, because 0 would mean that there is no particle in the box at all in any of these nx, ny or nz, and we start from say 1 1 1. So, 1 1 1 would be the ground state, and then 2 1 1 or 1 2 1 or 1 1 2 is the first excited state, and so on. And you see that apart from the ground state, now there is a degeneracy, and this degeneracy is what we are talking about, that is the corresponding to different quantum numbers, which correspond to different quantum states or wave functions, they have the same energy. For example, say these nx square plus ny square plus nz square, it corresponds to 6 is equal to 6, then we can have 2 1 1 1 2 1 1 1 2. So, this is these three are degenerate, and this degeneracy because they correspond to different wave functions. What wave functions do they correspond to? So, psi of for this particular thing, say 2 1 1, that corresponds to root over 2 over L whole cube, and a sine 2 pi x by L, sine pi y by L, and sine pi z by L. And similarly, the psi 1 to 1 would correspond to root over 2 by L whole cube sine of pi x by L, sine of 2 pi y by L, and sine of pi z by L. Okay. Similarly, the last one, which is 1 1 2, would correspond to root over 2 by L whole cube. I am so sorry, it should be whole cube, and sine pi x over L, sine pi y over L, and sine 2 pi z over L. Okay. So, they have the same energy which is given by 6 pi square h cross square by 2 m L square. Okay. So, they have the same energy, and that is why they are degenerate. Now, if you have a large number of particles which are now fermions, okay, and you cannot put 2 fermions in the same quantum state, one electron can only occupy one state. So, that way if you start filling up, and if you think of homogeneously filling it up starting from 0, that is n x equal to, or rather the lowest energy, say for example, okay, let us take n x equal to 0, n y equal to 0, n z equal to 0. That does not correspond to anything physical, but say that is the origin of this coordinate system in terms of n x, n y, and n z. So, you fill them up homogeneously from the center or from the origin, and this will take the shape of a sphere. So, in 3D it will be like a sphere. So, and the sphere, if you have n particles in a volume V, you can fill it up, all those n particles within a sphere of radius, which is called as a kf, or the Fermi momentum. So, we are filling it up in momentum space because this n really connects to the momentum variable. Okay. So, we number of allowed k points within a radius kf, and this radius has a special name called as the Fermi wave vector, and will be used heavily in all all discussions of the Fermi system. So, this is called as a Fermi wave vector. And how many allowed values are there? So, we have a V over 2 pi whole cube and a 4 by 3 pi k f cube. Okay. So, V over 2 pi, if you remember that if you walk a distance 2 pi over L, you get 1 k point. So, if you walk unit distance, you get L over 2 pi k points, and in 3D it is V by 2 pi whole cube. If you want, you get 1 k point, and you multiply that by the total volume of the sphere, and this gives you kf cube equal to divided by 6 pi square into V. So, if you equate this n equal to kf cube divided by 6 pi square into V, that will give you the density, and I will just by hand multiply a factor of 2, which stands for spin degeneracy, which means that there are spin up particles and spin down particles. Okay. We talk about spin half particles. So, the spin angular momentum is half. So, this is the spin degeneracy, which is nothing but equal to 2s plus 1. Okay. So, if you do a simple calculation of this, that is, in order to find kf, you find kf to be equal to 3 pi square n whole to the power 1/3. Okay. So, that tells you that if you want more particles to be accommodated, is just that the Fermi momentum, or the sphere, the radius of the Fermi sphere, that just increases as n to the power 1/3. Okay. And we can also define, so this is that Fermi wave vector expression. Now, we define the Fermi energy. We will show in the distribution what Fermi energy is. So, Fermi energy is nothing but h cross square kf square over 2m, where m is the mass of these electrons. So, this is equal to h square over 2m, and we have a 3 pi square n whole to the power 2/3. Okay. So, that is the Fermi energy. So, the Fermi energy grows as n to the power 2/3, which means that the if you have more electronic densities or more number of electrons, then you have larger Fermi energy and so on. So, if you put this typical values of this n, which is, as I said, it is about 10 to the power 24, put the mass of the electrons, the Fermi energy comes out as 5 to 6 electron volts. We will see that. Okay. And that is a very large energy. In solid state physics, 1 or 2 volts of energy, electron volts of energy is very, very large, and that is because 1 electron volt is equal to approximately equal to 11,600 Kelvin. You can understand how large the temperature is, because this is not even, the core of the sun probably would have a temperature something similar to that. Okay. It is only the periphery of the sun is about 6,000 Kelvin. Okay. And what is room temperature? So, room temperature is nearly 0.025 electron volt, which is 300 Kelvin. So, what I do is simply take the electron volt and connect it to kT. K is the Boltzmann constant, and find T, and this is just the hand waving, or rather this is almost learn it by heart, that these are some of the numbers that we are interested in. So, while high energy physics talks about very high energy such as GeV and TeV and all that, we are very content with these scale of energies, like 1 electron volt is a very large energy, and typical semiconductors have an energy gap which is of the order of 1 electron volt, or a little less than that or a little more than that in some other semiconductors. So, you can never make a material conducting, such as a semiconductor conducting, by applying temperature, because you will melt everything in the universe by if you apply this kind of temperature. So, 1 electron volt of energy difference is very large energy difference. Okay. So, so this is the the Fermi energy and so on. So, these we can find out the ground state energy, for example, for a degenerate Fermi gas. So, what we are trying to calculate is, you call it E0 or EG, up to you. You can just simply get this 8 pi V over H cube and 0 to Pf. We are not writing in terms of Kf, but you can write it in terms of Kf. We simply do this P square by 2m, and we have a P squared dP. So, this 4 pi P squared dP, the 4 pi has been taken out. This 8 comes because there is a 4 pi and then there is a 2 factor due to spin degeneracy, and that is how this is. So, this is very simple integral. It is like P4 integral. So, you will get a P to the power 5 and so on. So, if you simplify this, the this ground state energy per particle comes out as 3 by 5 epsilon f. Okay. So, that is the Fermi energy. We probably have written down, yeah, Fermi energy is EF epsilon f. So, epsilon f. So, it is the ground state energy of free Fermi gas is very, very large. Okay. And it is independent of temperature, because there is no temperature that is equivalent to it. If you convert that into a temperature scale, so the Tf gives the temperature scale, and which, as I said, is of the order of 10 to the power 5 Kelvin. Okay. So, if you want to calculate the pressure, so pressure due to the Fermi gas is call it a P0. So, the at T equal to 0, or we call it the very low temperature, because I said any temperature is like 0 temperature, any accessible experimental temperature is like 0 temperature. So, we write T equal to 0 nevertheless. So, this if you calculate it and use this formula that we have derived a number of times, at least for the non-relativistic case we have derived it earlier, which was 2/3 u by v, where u is nothing but the internal energy is nothing but the ground state energy here, and this is equal to 2 by 3 into E 0 by V, which is 3 by 5 and E f, and then this goes, and it is something like that. So, it is 2 by 5 epsilon f and things like that. Okay. So, so this is that pressure due to Fermi gas, and as you can see that this is very large, and this pressure is due to the hardcore nature of the particles. That is, they exert enormous pressure to another electron coming in the same quantum state, and it does not allow at all. It is like infinite pressure, so that no other particle can come and occupy the same quantum state, and that is why this energy is so large and so on. Okay. So, this epsilon f really goes as n to the power 2/3 and so on, and similarly we can find out that how this pressure, ground state pressure with density goes as. Okay. This is very simple. Now, let us talk about the Fermi-Dirac distribution, and in short we write as a FD distribution. And this distribution is very distinct from the Bose distribution, and it is at t equal to 0. So, this is at t equal to 0. This is that f of epsilon, and then you have epsilon and so on. So, it is just a step function. So, for all epsilon lesser than epsilon f, all the states are occupied. Okay. So, this is all occupied states. Okay. And all states here are empty. So, this is at t equal to 0, and what happens at t slightly different than 0 is that so this f of epsilon to be and now what happens is that this one slightly broadens and goes like this. Okay. So, say here there was used to be a sharp drop, and now it got bent from there. Let me draw a little better here. So, it gets bent there, and a little bit of spectral weight gets transferred to larger energies, and now we call this all the states below mu are occupied. So, we have two things, which is mu called as a chemical potential, which we have defined before many times and in various contexts, this chemical potential, and we have talked about Fermi energy, which is in the recent past. So, Fermi energy. How are they related? Mu is equal to epsilon f at t equal to 0. Okay. And at t not equal to 0, that is the temperature not equal to 0, Fermi energy is not well defined. Okay. And so, basically the chemical potential is still well defined, and which tells you, or rather which defines the highest energy state that is occupied at any temperature, still well defined. Okay. So, now as you understand that this really deviation from t equal to 0, that is this distribution becoming slightly curved from the top, and then a bit of spectral weight is appearing at the bottom of the tail. This happens at large temperature, and in fact, if you simply talk about increasing the temperature, it sort of goes, I have to be a little careful because it goes like this and so on, And in the limiting case, of course, we know that the classical statistics would prevail, but we know that now the classical statistics, in order for it to prevail, we need to go to very, very large temperature. Okay. So, that kind of temperature like 10 to the power 5 Kelvin, 10 to the power 6 Kelvin is not achievable in under any experimental conditions. So, that is why we said that for all all practical purposes, this degenerate Fermi gas is considered as 0 temperature. We still are not, this has to be smooth and so on. Okay, this is probably slightly better. And so, that is where that is how the Fermi distribution looks like, that is how the Fermi energy and the chemical potential are defined. They both mean the same thing, but the Fermi energy is strictly defined at T equal to 0, chemical potential is defined at any finite temperature. They mean the same thing, they denote the maximum, the energy up to which the electrons occupy and above which they are empty, or you can say that it is the energy required to add one particle to the system, because you see that is the maximum energy levels which is occupied. All the energy levels that are here and here, they all have one electron each. Okay? And if you are thinking of spin, then they have 2 electrons each, with one with upspin and one with downspin, and all these are completely filled. And for you to add one electron to the system, it cannot go anywhere, but it has to go to the higher energies, because by creating more quantum states. Okay? Because there is nothing that is available to them, because they are completely filled. Think of a room that is completely filled, and if someone comes, that more space has to be created, because this room would not accommodate this an extra person. So, the walls have to be moved. It is just like that, the walls have to be moved, wall of these step functions, that has to be moved in order to accommodate extra particles. So, that is the same meaning that we have for. So, at a finite temperature, if you want to calculate quantities, say for example, we show this say n. How do you calculate n? That is 2 of f epsilon, g epsilon, d epsilon, and this f of epsilon is nothing but the step distribution, which is written as exponential beta epsilon minus mu plus 1. Okay. So, that is the distribution. This distribution is important and has to be distinguished with the Bose distribution, where mu had to be negative and would be only approaching 0 in the quantum limit, extreme quantum limit, whereas mu is positive here. It is on the right side, mu resides on the right side of the diagram, and that denotes the largest occupied state, and you have this at t equal to 0, which is 1 over kT. All states which are epsilon greater than mu are unoccupied, and all states which are less than mu are occupied. So, this mu at t equal to 0 is nothing but epsilon f. Okay. So, you can see this easily if you write this down as epsilon minus mu by kT and plus 1. So, if you put t equal to 0, this would like to be infinity, but only infinity when epsilon is greater than mu, and in that case this is equal to 0, because 1 by infinity is 0, the plus 1 does not matter. But if t is 0 and still epsilon is less than mu, then it is exponential minus infinity, which tells you that the occupancy is equal to 1, and that is why we see that step structure that you see here. So, I will just write that once again. For epsilon greater than mu, f of epsilon equal to 0 for reasons that I just told you. For epsilon less than mu, f of epsilon equal to 1. Okay. And it has a sharp discontinuity at t equal to 0, and this is very important. And that discontinuity, if you take a derivative of the Fermi function, there it looks like a delta function. Okay, so this is elementary discussion about free Fermi gas distribution and so on. One more important thing, or rather like a hand waving thing we can talk about, and we just draw this distribution once more. And suppose if we want to know that what is the specific heat due to electrons at T equal to 0 or at T equal to 300 Kelvin, as I said, it does not matter. So, you have to understand that if you a specific heat is the heat required to raise the temperature of the body by a degree, which means that the electrons from this region would be excited and they would go to the higher energy region. So, this at a temperature T, this is width is like is of the order of kT. So, they would come here and they would like go to this thing. Let me write it with or they make the hatches with a different sign. So, the black ones is where the electrons come from. If you increase the temperature just a little bit, and the red region is the ones that they go to or they occupy at that temperature. So, this is of the order of kT, and so this is the so what is the fraction of these particles that are excited? It's kT by kTf, okay, but Tf is the Fermi temperature. So, each of these have an energy which is like kT, and that is why this whole thing, so the energy goes as T square, and so the specific heat would go as T. That is the relation that we all are aware of, okay. In some sense that if you have studied Fermi gas before, then you know the specific heat due to electrons is that the variation with temperature is linear in T. So, for a material, if you are doing an experiment and you want to find the specific heat actually goes as alpha T plus gamma T cube, and this is the electronic contribution and this is the phonon contribution that we have seen. That is the Debye's theory, and this alpha T is the linear in temperature, which we just shown in a hand waving way and can be derived. Okay. So, once you are familiar with this, this is all taught in the first course of solid state physics while you learn metals. Let me go back to the statistical mechanics of the free Fermi gas. And the way we have done it earlier, we will do it the same way. So, log of Zg, these are starting point as you have seen earlier for the Bose case. This is equal to sum over I log of 1 plus Zf exponential beta epsilon I. Epsilon I are the the single particle states. Zf is still the fugacity, which is exponential beta mu, and we can write this equation as equation 1. So, we can write down the number equation as this, and there is a sum over I, and this is like a sum over I and the distribution. We are not really writing the spin degeneracy here, but you can write a factor of 2 if you wish. So, this is say equation 2. So, we convert this summations into integrals, and we can write down P over kT equal to this is you can write a g over lambda cube. I will tell you what g is. Usually it is written with a g, and g is that the degeneracy, and in particular you may want to talk about the spin degeneracy. So, it is g over lambda cube f 5 by 2. You can remove g also if you wish, if you are not talking about spinless, if you are talking about spinless particles. So, n over v is again g over lambda cube f of 3 by 2 Zf. We are writing Fermi functions, Fermi integrals with f, and Bose integrals were written with a g. Okay. And f of n ZF, that is a Fermi Dirac integral, is called as a Fermi Dirac integral. So, this is equal to 1 by gamma n, there is 0 to infinity x to the power n minus 1 dx divided by ZF inverse e to the power x plus 1. Of course, the connection has to be set that x equal to beta epsilon and so on and so forth. Now, this for small ZF, it has this expansion as 2 to the power n plus ZF cube 3 to the power n minus and so on. So, it is alternate plus minus plus minus. So, these are this is the expansion in for small ZF, which of course corresponds to the classical limit, but then we know that in Fermi systems the classical limit all accessible temperature regime is actually falls in the quantum limit. So, what is the internal energy of this Fermi gas? Once after we have given an introduction to the Fermi Dirac statistics and so on, we are getting into this formal mode of getting the physical quantities, that is from the log Zg. That is the statistical tool that we have developed over this last so many weeks, and that is what we want to stick to. Otherwise, every solid state physics book has a derivation in terms of for the specific heat or for say internal energy and ground state energy and pressure and this and that and so on. I think there was a just go back, and I believe there is a n missing here. So, that is I think missing here. Okay. So, that n is the density. So, actually P 0 goes as n to the power. So, this 2 by 3. So, 2 by 3 plus 1. So, this is like n to the power 5 by 3. Okay. So, that is the ground state pressure. So, I missed that n, which is the density. Okay. So, the internal energy, how do we get it? We get it using our very familiar form, which is log of Zg, this del beta log of Zg and Zf and V being constant, and a little bit of simplification can be achieved when you do a del t of log of Zg with a kt square there and Zf V. So, this can be written as 3 by 2 kt this g v over lambda cube f of 5 by 2 Zf. That is the Fermi integral that we have just defined in the previous slide. So, this Fermi integral with Zf inside and n is equal to 3 by 2 or 5 by 2, depending on whether you are talking about pressure or internal energy and the number of particles. So, this is the expression for internal energy. Let us call it as equation. So, we have equation 1, 2, 3, 4 and we have say for example 5, and we can use P equal to 2/3 U by V. This is universally true for all non-relativistic gases, and the factor is simply replaced by the coefficient is replaced by 1/3 for the this for non-relativistic and 1/3 is for relativistic. Okay. So, if you differentiate 5 with respect to this, let us call it a 6. So, differentiate with respect to t and use this formula. Again, this formula has been or something very similar has been used for the Bose gas as well. It is del z del t at a constant V. So, this is equal to minus 3 over 2 t f of 3 by 2 z f divided by f of half z f. Okay. Now, the Fermi integrals replace the Bose integrals. If you use this and take a derivative of u with respect to t, then what you get is the following. So, you get a C v equal to n k and f of 5 by 2 z f divided by f of 3 by 2 z f and minus 9 by 4 f of 3 by 2 z f f of half z f. Okay. So, this is equation 7. I hope I have written 6. Okay, 6 is there. This is 7. This is the expression for the specific heat at any temperature of a Fermi gas. You just have to use these Fermi integrals to know their the temperature, exact temperature dependence, and the free energy. Of course, you can write down the free energy. They are not very important, but sometimes for some particular reason that you may need this. So, a free energy F is equal to mu n minus P v, and that is equal to n k t log of z f and f of 5 by 2 z f and f of 3 by 2 z f. Okay. That is your free energy. We are not doing anything more with this, just getting the expressions in terms of the Fermi distribution function or the Fermi-Dirac integral. Now, to get the exact temperature dependence at all temperature, you have to expand this and for z f to be small, it is easy because all these things will become just simply z f. So, z f will kind of cancel, and you can see that it becomes 1 minus 9 by 4. There are these things will sort of this will go to 0, rather this f half z f. All these will have to be calculated. I mean, they are general expressions as a function of temperature, and that is why. So, this is the most general expression that you get it at all temperatures, okay? Low, high, very low, and all that. Okay. And similarly, the entropy can be written as so the specific heat and entropy is written as S equal to U minus F divided by T. You got U and you got F both, and then divided by T, which is simply nothing but N k, and then we have a 5 by 2 f of 5 by 2 z f f of 3 by 2 z f and so on, okay, minus log of z f. Let us call this as 9, and so these are some of the expressions that you have. Now, they are of course sort of the Fermi gas, or rather we are interested in most of the cases as low temperature properties of these things, and in order to get the low temperature properties we need these forms of these Fermi-Dirac integrals, and the expression of the Fermi-Dirac integrals as in the finite but low temperature. At t equal to 0 it is easy, but at finite and low temperature one has to do a Sommerfeld expansion of these Fermi function. I mean, I just write these Fermi functions, or you call it the Fermi-Dirac integrals, which are really the integrals that we have introduced, are needed at low but finite temperature. and this is the limit that is of interest to us, okay, because the properties of these systems are very important at low temperature, because the quantum effects dominate at low temperature. At very high temperature, of course, classical limits would dominate. Even if we understand that even room temperature is same as 0 temperature for electrons, but what about other properties that are twined with this? They are mixed with this. So it's not. So we do these experiments. Any experiments in solid state physics is done at a reasonably low temperature to see the quantum behavior to be to be perceived. So these things can be written as this f of 5 by 2 ZF. This is equal to 8 over 15 root pi. These are the Sommerfeld expansions. We do not get into the details of that. These are mathematical properties, and they are quite important for many usage, and we will sort of see, but we will keep only the leading term, one term after the leading term. That is important, because this one will give you exactly the behavior at t equal to 0. Anything more than that, you want you have to go to one, at least one order, and f 3 by 2 ZF is equal to 4 by 3 root pi, and log of ZF 3 by 2. These are only given information, they are not derived. If you really want to get into this, you can look at this Sommerfeld expansion of the Fermi-Dirac integrals, but they are only the results are only useful to us, and that is why I simply write these expressions, and you would only need them for getting results at small but finite temperatures. So, f half, these are the 3 that are involved, and this is equal to 2 by root over pi, and there is a log of ZF to the power half, and 1 minus pi square over 24 log of ZF to the power minus 2, and plus all that other terms. So, if you want the expression for the density of particles, simply take the f 3 by 2 and put it in this n by v equation, which is 8 pi over 3, 2 pi over h square 3 by 2 kT log ZF whole to the power 3 by 2, and 1 plus pi square by 8 log of ZF to the power minus 2. Okay. And there are other terms which you may not want to write. So, in the 0th approximation, that is at 0 temperature, we have said that. So, in the 0th approximation, what do we have? We have the kT log ZF is equal to mu, which is equal to 3 n by 8 pi whole to the power 2 by 3, and 8 square over 2 m, and this is nothing but epsilon f. Okay. So, at t equal to 0, mu is equal to epsilon f, which is what we have said earlier, that they are not distinct, and this is equal to mu. And so, if you neglect all other terms, you get this one term, and that gives you this kT log z. There is a t that is missing here. Okay. So, that is your epsilon f, and at the first order, that is at a temperature that slightly differ from t equal to 0. Okay. So, taking the first order correction to this, we can get this as, so we have this mu, which is equal to epsilon f, that is leaving the first term, we have 1 minus pi square by 12 kT whole square, kT by epsilon f whole square, and then there are other terms there. Okay. So, at T equal to 0. So, put the second term equal to 0, mu equal to epsilon f, which is what we have claimed. At T not equal to 0, mu deviates from epsilon f, we have said that, but how it deviates is shown here, that the first order correction to mu compared to epsilon f is of the order of t square. Okay. And this can be carried on to the internal energy as well. So, we can write down the internal energy expression is U over n is equal to 3 over 5 epsilon f 1 plus 5 pi square by 12 k T by epsilon f whole square and plus all that. So, what I mean to say is that suppose this is the ground state energy, and this ground state energy per particle is 3 by 5 epsilon f. Now, this is easy to get because you have this E 0 equal to epsilon g epsilon d epsilon and from all the way from to epsilon f at t equal to 0, okay, known, you get the first term. What's the correction? So, correction to the ground state energy would be, or rather the total ground state energy at T not equal to 0, you will have to add this Fermi function here, and this is the function which is 1 divided by exponential beta epsilon minus mu plus 1. Now, epsilon is simply epsilon, and g epsilon is epsilon to the power half and so on, and if you try to do this integral, it is going to be very difficult. Okay. And an exact solution is probably available, because that is what people have done for a long time, that dealing with this integrals and trying to find a closed form for that. And so, if you wish to know that was the first order correction to this E 0 compared to the t equal to 0 value, which is 3 by 5 epsilon f, this goes as 5 pi square by 12 and a correction which is of the order of t square. So, if t is not too small, that is if it is not cannot be neglected, then include it, and if you are really at very low temperature, then of course you can. Suppose you are at 50 Kelvin and the classical limit is at 10 to the power 5, 10 to the power 6 Kelvin, and so I mean classical limit means the epsilon f, which is what you compare it with. So, if KT is like say 100, 150 Kelvin and epsilon f is like 50,000 or 1 lakh Kelvin or 0.1 million Kelvin, then of course it can be neglected. But if you are still at say 1000 Kelvin or 5000 Kelvin say for that kind of temperature, then that thing can be included. But of course, there is nothing called 5000 Kelvin in the experimental realm. Okay. So, we can in that case we can neglect it, but at least it gives you the first order correction to the t equal to 0 result. Okay. And similarly, for the pressure, so this P is equal to 2/3 U by V, and this is equal to 2/5 n epsilon f, a result that we have already seen, and it is 1 by 5 pi square by 12 and k T square by epsilon f whole square, and you have other terms which can safely be neglected. Okay. So, the leading term always gives you t equal to 0 result in all the cases that we have seen, and so the CV finally can be written as it is n k pi square over 2 and k T over epsilon f. So, this is a result that we are interested in, and CV for a fermionic system or an electronic system at low temperature, it goes as TQ. Okay. So, this is by and large the story of thermodynamics for a free Fermi gas. Okay. And it is very important to realize that even at room temperature, we are really talking about the Fermi gas as if it is highly degenerate and at very low temperature, that is at T equal to 0. If you want any correction due to this really T not equal to 0 and T equal to 300 Kelvin or at least 150 200 Kelvin, you can consider these corrections to these expressions of pressure, internal energy, number of particles, etc., that we have just given. Okay. So, we shall stop here and continue with some more applications of this Fermi-Dirac statistics, and as I said, one of them would be the paramagnetic or the Pauli susceptibility of due to the free electrons, and we will also talk about the white dwarf stars. Okay. We will stop here. Thank you.